So this is a SIMD algorithm I developed. It basically generates an array of bits where each set bit indicates a indicates a string. So if we just do a fresh build, okay, we do a fresh build and then we run it. Let's confirm it. So there's the first string is three Fs, which is correct here. Second string is a hello world, and then followed by three Fs here, and then followed by another three Fs here, and then last one's a hello world here. So that's correct. So that's how that works. And I'm going to explain it because explain how this works. Because of this thread here. So I have two approaches. This is the revised approach down here, and this is my original approach. Well, it's not my original approach. I kind of changed a bit of it, but the changes didn't really change the big idea that much. But anyways, so let's step through this. Skip that part. Let's skip to a string. Okay, we are on a string now. So actually, let's skip that string. Okay, so this is an interesting one because it's an unterminate string within this batch. Well, okay, we load 16 bytes first into x0. Sorry, because we're working with 16 bytes, and we want to detect quotes and escape characters. There's a bug where I don't detect consecutive backslashes. I don't want to do that at the moment. I just want to show, okay, this is okay. Convert the marks to bits, the quotes and escapes, so everything that we marked into bits. R1 and R2. And of course, if the previous batch ended with an escape character, then the first byte of this string would be escaped. Of this batch, the first byte of this batch would be escaped. So this part handles that. And then if the last byte of this batch is an escape character, well then it means it's escape. So this is what that code does. And we erase the escape quotes or the escape characters. And okay, so this is the smearing. So let's look at MS Paint. So the original idea that my main idea by just brainstorming various permutations, honestly, it was kind of brute force. But the original idea was if we had like shifts, right shifts and left shifts. I probably should use these arrows, but whatever. These right and left shifts. Well, there's this overlap here. There's this overlap here. And that overlap is actually where the strings is. The string is. And so that's what I wanted to get. So that's what the smearing is for. I did the XORs. Because if there's two consecutive quotation marks, well, that means it's a complete string, right? So if we just imagine, probably expose a bunch of stuff. Okay, so if you imagine, like, let's just make up a string here. 4, 1, 2, 3, 4. Okay, so the first right here, and we're gonna do here. So if you imagine the string here, so these ones indicate quotation marks. Here, actually, I want to move this here. All right, so we start off the least significant bit, or the rightmost digit. Right. So we XOR it. It's fine. It's nothing. But once we get here, once we get into the one here, we start to smear it. So this is going to turn to 1. This is going to turn to 1. This is going to turn. But then we encounter a 1 here. So that means two consecutive ones. Means it's a string. So effectively what we did is detect all the quotation marks. Detect the quotation marks, excluding the last quotation mark. And as you can see, if you notice, I I overlooked that I didn't actually need this other half, this other bidirectional half. I didn't need this overlaps, the two shifts, the smearing, because I only exclude the terminating quotation mark, um, which is funny. Unless I'm overlooking something right now. I overlook so much, but yeah. So let's observe this happen. So yeah. So we skip the F, we skip the left parentheses, is indicated by here, 0, 0, and the remaining shit. And the remaining is set bits, ones. And then we switch it to odd. And if there's an odd amount, or we take the odd, okay. And then, okay. So this is interesting. Originally, I did pop count and just pop count to count the number of set bits, to see if there's even an odd amount of quotation marks. But I didn't know this until I talked to Mr. Langdell. Langdell. I don't know if that's how you pronounce the first name, or maybe the last name. Langdell, whatever. Mr. Langdell. I didn't realize until I talked to Mr. Langdell that it was actually parallel prefix sum. That this was a parallel prefix sum. I didn't even know that this thing existed. So this left part here, this left shift right, is a parallel prefix sum, which sums up the bits and puts them at the left, the most significant bit, the left most digit. And so we extract that here, and it tells us the parity, if it's even or odd. So that's what that does. And then the right side here is actually the gray codes. It's actually gray codes that's striped here. I didn't know that, but yeah. And if it's odd, we flip it. We flip this set here. Where is it? Okay. We flip it here, so then we also exclude the initial quotation mark. And then we finally get the overlap. We select the overlap here, which by doing the and. So what that does. And then if we're continuing, we just flip it. That's simple. And then if it's two odd numbers, then that means they add up to an even number. So that means we've completed strings. And then we just include the quotation marks, this is completely redundant. So I overlook a lot of stuff. I do a lot of redundant stuff. I was very excited that it actually finally worked, so I didn't revise it. But yeah, but that's how that works. And then let's look at the next batch so we can see how it continues. Kind of a continuation. Skip this part. Okay, we look at the smears. So we have the first two are unset because they're input in a string, and then we set, which are effectively essentially outside of string, pretty much. Not actually, but that's what it thinks. And then we select them, and so instead it's the zeros are within the strings, and the ones are outside of strings. And then we flip it if we're continuing a string. So then 3 now it's correct. So 1, 2, 3, and then we 0 here because of space and whatever. Then we include the quotation marks, and yeah, it's pretty cool. So like I said, there's a lot of redundancies, which is why this revised version, it's a lot simpler and it's a lot more elegant, to be honest. We also don't need this. Wait, do I? I don't remember. I'll check that later. But yeah, that's actually how it works. There's a lot of redundancies. So this is why you need a second perspective. That's why you gotta ask. You're interested in this sort of stuff. I like your input. I didn't see this until now. Because let's look at this. He saw this problem. It's a lot simpler. I don't know if I think I actually got to his same conclusion actually. I don't know. I didn't really read this much because he uses AVIX 2. I use SSE 4.2. Um, and this algorithm is part of a larger project of mine, um, where I do where I tokenize, but I tokenize branch free and table free. No, zero tables, zero branches, and I use SIMDs to basically do this to do stages of just these detections and transformations. As you can see here. So this part is the original. Well, it's actually not the original because I rewrote this a bit, but process tokens. This is where we process the quotation tokens, which is also done via the approach, which is much smaller, much nicer. And it is over here, process simple tokens, which is tokens that are like one character or 1 byte long, and these are complex tokens, so that's identifiers and keywords, whatnot, and numbers. We don't detect equal signs and like multi-byte operators, because you can do that here, but that just makes things complex. And no, you can't do that here. Sorry, because then it would think that these operators are included in the identifiers, for example, or in the numbers if they're contiguous each other. I should now realized. But I try to be clever here. I do like a lot of shortcuts. Because I like, for example, I don't do keywords. I don't detect keywords here. Keywords, numbers, and words are effectively the same. They have the same transformations. And in simple tokens, to have like complex operators like XOR equals or shifts, you want to manually just detect. Okay, you want to manually just mask them and see if they're contiguous, or you do probably better do state machine, whatever. There's also another implementation I have of a tokenizer where there's complete is use a table, which may I use better. I don't know. This is I don't think this is practical, except for this because this is actually works. And well, I know it's practical because well, I know it's practical because Geoff Langdale did this, which is really cool. Which I didn't know until now, until yesterday. But I just wanted the reason why I did this, it's not for practical reasons, but I wanted to see if it's just possible. And it is. So and then you expand your horizons, you expand the possibilities of just just all the branch free possibilities and all this cool stuff. It's all this cool stuff. Okay. I think this is enough. I recorded this like so many times. The first time I didn't even my microphone wasn't even working. So hopefully it's actually working. But hopefully I talked about everything that I want to talk about. But yeah.